Thank you for coming to today's webinar, The System as Code Paradigm, Transforming System Engineering, Building Superior Systems Faster. Dr. Juozas Vaicenavicius is a CEO and co-founder of Sensmetry. Juozas is a mathematician, engineer, and entrepreneur passionate about effective, rigorous management and involvement of complex systems. His engineering and technical leadership experience spans over a decade and covers multiple industry verticals, including automated drying systems and advanced satellite constellations. Juozas has contributed to industry-wide technical standards development, such as OMG's SysML v2 and the ISO 21448 SOTIF, which is a central automated driving safety standard. He also has published research in top journals and conferences. He completed his PhD in mathematical statistics at Uppsala University and prior studies at Oxford University. Thank you for being with us here, Juozas. I'll hand it over to you.
Thank you. It's a pleasure to be presenting at this webinar. So I'll share my screen now. Can you see it as well?
Yes.
Excellent. So let's start. So we at Sensmetry, the company behind a tool called SysIDE to enable this, what we call the system as code paradigm. And that's what we'll be talking about today. And we believe that the systems engineering discipline is undergoing a paradigm change that can enable all of us to build superior systems much faster. So let's go on and see what it is. So if we try to introduce some change, it's typically for reasons. So let's start with an introduction. Let's define the problem that we are trying to address, and let's look at the proposed solution. So paradigm change is due in systems engineering, and let's see why it is due. And the reason is simple, that established ways of doing product or systems engineering are still highly manual and inexact, and they are slow and costly. The situation is that even though we managed to make machines, and by machines I mean computers, do most of the sort of execution work, we still, when we do systems engineering, when we do product engineering, we still do it in a highly manual, inexact way, which is slow and costly. And this has been and is identified by many people and many companies. And one concrete definition and identification of the problem comes from the US Department of Defense, where they define this instruction directive, what they call digital engineering, and the exact number is 5097, to speed up the development process, so that superior systems can be developed much faster. But that concept, and that's what we see on the right in this this picture, this famous picture from that report, is very conceptual. It says that digital twins should be utilized, digital threads should be there for traceability, system information should be in models, not in vague text documents or vague diagrams. And if all of these things are sort of machine processable, machine interpretable, then we can outsource a lot of the work to computers that we as humans typically do, and that's why we can create such superior systems much faster. So what we, Sensmetry, are proposing is a concrete technology to make this happen. So we need a paradigm, and we call this system as code paradigm. We need a language to express this digital engineering approach, and this language is SysML v2 for us. We are together with the industry partners, the developers of this new language for systems engineering, and we need a tool suite. And for us at SysIDE, we've put our heart and soul into developing this most performant systems engineering tool. And SysIDE stands for Systems Integrated Digital Engineering. That's the holy grail of our tool suite. Okay, so let's go through each ingredient in order. So what is the system as code paradigm? So system as code is for both humans and machines, and is meant to apply it across the system lifecycle. So in particular, what we mean is that system definition is in rigorous as code language and interpreted and understood by both humans and machines in the same way. This is a critical ingredient because without having a common understanding by both humans and machines, we cannot work together, and take advantage of computers doing the work that we, product engineers, system engineers do. This system definition should be in declarative form, which adds a lot of clarity and allows to focus on what my system shall be and shall do rather than how. And this is very, very powerful. So what I mean in particular example, for instance, is that the fact that I want to have particular system observability property, like I want to know what's the temperature of my system component, should not be defined in C++ code that there should be a signal in C++. That's a software language. It should be defined within a systems engineering discipline that I want a signal that reflects the temperature of my system component, and that it should be updated at that particular frequency and so on. And then software engineering discipline would take responsibility to implement that feature in whatever language and technology would achieve that best. And the third ingredient, for us is that the system definition is up to date across the system lifecycle, and it reflects both intended and unintended systems changes. So, example of an intended system change is a system update. So we release a software update, and now the definition of our system, let's say a satellite or a car, changed, and that's reflected in the system definition. So it remains authoritative source of truth across the system lifecycle, from the design stage to operations and decommissioning. So that's what we mean by system lifecycle. And sometimes there are unintended system changes. For instance, if a system is a satellite, a particular component started to malfunction or even fail, we need to update the system definition to reflect the reality. The system is no longer the one that was designed, it's a different one. That particular component is no longer functioning. Right, so that's what it is for us, and that's what we argue that it should be. And there are a lot of benefits if we make this happen. So the benefits are efficiency and speed through unlimited automation and generative engineering possibilities. And why it's unlimited is because through this rigorous as code language and this information represented in this rigorous as code language throughout the system lifecycle, we can do with computers and with AIs anything that a human engineer can do. And of course, we can do this much faster and in a much more efficient ways. Now, it also streamlines collaboration through this unifying as code knowledge representation and also workflows. So what is happening, it's very valuable, is because it removes the software hardware boundary where both hardware engineers and software engineers can work in the same S-code way using the same tools and the same workflows. And one concrete example, for instance, is safety analysis, where both software and hardware are very important, and you have to think about safety both across hardware and software, and you should have a unifying model of that, and that's really streamlining and collaboration very much. Also, there is no vendor lock-in because it's purely human readable and as text, as English is or as French is. So that's an obvious advantage, but there is another not so obvious one, that even if it's, even if the tool is, for instance, a graphical modeling tool, you still get attached to a particular way, the functionality is, is represented in that tool, and that each graphical tool has a different user interaction. So there is a lock-in through user experience. But what we know from software engineering is that working in S-code way, that user interaction-based lock-in is almost non-existent. So, within the same company, people use many different IDEs, and it's, quite easy to switch from one, integrated developer environment to another one. There's one very important philosophical, almost, aspect that, builds trust in the systems we create, is transparency and accountability. And that, if we embrace this as code paradigm, and and this goes across a full stack, defined as code both in time and both defined as across a full stack and in time. So what I mean in particular is that if the system is defined as code, so one can inspect as a human being in a human interpretable representation, that's this textual as code representation, what my system is and what it does. All the way through the full stack and cyber physical system, from what are the different components to what exactly software is doing, down to the microprocessor level. And that's really important, for the really critical infrastructure that we are building, that we are not locked out, and we are able to go and inspect as human beings exactly what my system is, and actually in the worst case print out everything on a piece of paper and go with a pen and paste pencil and to understand how it's exactly doing things. And last benefit among many that we mentioned is reusability of the system information across the system lifecycle and beyond. So what we here mean is that the same system definition is utilized both when defining the system, also for any type of simulation, any type of testing, also for through operational phase and beyond, when there is another generation of the product being imagined, and all that reusability can be achieved because it's all in this comfortable and convenient format in this textual representation. Okay, so I spent quite a bit of time on this, but I think it's important that to stress that this is a paradigm. It's you're trying to make things simple, clean, and have this foundation on which this speed and efficiency and quality in systems and engineering can be achieved. Okay, so the second beauty of SysML v2 is the language. And SysML v2 is this rigorous unifying language for systems engineering, and it's ideal to achieve the system as code paradigm. Largely because it's been engineered with these requirements in mind. So in the past, and still present in most companies, we have a situation on the left side of this picture of the slide, where the system data is disintegrated, and there are many non-interoperable or badly interoperable tools. So these are all separate boxes. For requirements and one tool, for structural behavioral modeling another, for analysis yet another, and visualization yet another, and in some success story examples, they are being able integrated, but more often than not, these are disintegrated, and exchange happens through emails and sharing files and these type of old-fashioned approaches. The future that we believe in is on the right, which we have a single source of truth in rigorous language as code, and this allows for interoperable ecosystem without vendor lock-in. So everything that we have on the left is now expressible in this new language, SysML v2, because it's been designed goal. It's designed goal to be able to unify all this, and we don't, and we have all this integration, by design essentially. So we are, Sensmetry, actively contributing to the development of this language, and we are very excited that it's just been approved at the OMG by the architecture board. Essentially, the 2.0 version, the technical content has been confirmed, and the final official release in a nicely formatted document will be sometime in September or around that time frame. So the third ingredient, it's SysIDE, and that's our tool suite with an intent to liberate organizations to take full advantage of SysML v2. So SysIDE is a modern, flexible, performant, and interoperable SysML v2 tool suite aimed to liberate organizations to unlock unlimited automation potential across the system lifecycle and to make superior systems much faster. So in other words, it's really trying to enable the system as code paradigm, and to reap its benefits using SysML v2 as the main host language to express the system lifecycle concepts. And for us internally, the ultimate goal is speed and ultimate speed, because to make better systems faster, the most critical part is to be able to go from system definition update or system specification update to a prototype or deployment in 0 time. That's the ultimate goal. Because if we can do that, then we can explore the design space much better, and we can use algorithms for that. And also, the discipline changes very much through focusing on higher level requirements and evaluating and assessing and analyzing the prototypes. And we know from many success stories in physical systems development that this approach is leading to much faster system development. So this system specification update to a system prototype in 0 time, it applies both for algorithms trying to search the design space in a simulation, design optimization problem setup, or literally generating a real prototype and testing it and getting this very, very fast feedback loop. Right. So the picture illustrating all that is on the right. That SysML v2 plus SysIDE is meant to automate and speed up these iterations as much as possible. Okay, so now let's see what SysIDE is in action. So we'll have a quick overview and a demo, starting with the base functionality, and then we'll show a live demo. So first, SysIDE is not a new tool, even though the language is SysML v2 is very new, but it's been developed for a long time. So SysML v2 is now 7 years in the making, and since SysIDE has been released 2.5 years ago, the first version of it, and currently is the most popular SysML v2 modeling tool that was started by our SysIDE editor back in January 2025, and over that time, we won awards, presented at the main industry events, started actively developing SysML v2 as part of the object management group, and not only SysML v2, Caramel as well, but people are more familiar with SysML v2. So that's the language that we stress in communication. And 9 months ago, we started our early adopter program, in which we have over 150 companies already that used the features and build use cases utilizing that. And it's been a very exciting journey, and now we are launching commercial sales of the tool suite in July, so that's coming very soon. And again, to stress, Sensmetry developed SysML v2 and really aiming to support open interoperable SysML v2 ecosystem. So trying to enable all the creators to build SysML v2 related applications and use cases. So this is an overview of what the tool suite consists of. That's our offering. So the professional suite consists of the modeling application. So that's called modeler. Very intuitively, it's used for authoring, error checking, reviewing, and visualizing models effectively. And it's also supported by formal methods and AI. And on the modeler application, we are very happy to partner with Tom Sawyer that provides powerful model visualization capabilities within SysIDE Modeler. The engine and the sort of powerhouse of SysIDE is the automator. So, an analogy for SysML v2, it's like an interpreter or a querying engine for SysML v2 models. So, it provides analyzing functionality for models. It provides read-write access to the model, and can be used for anything that essentially an engineer would do manually, but through a programmatic interface. So it's available through a Python API, and that's how the majority of people are using it. And it's used to analyze models and optimize designs and automate workflows and develop custom applications. So it's really, that's one of the reasons it liberates organizations, because rather than waiting for a tool vendor to release some small feature that is needed, a company can internally very quickly prototype and build a small application using SysIDE Automator. And we'll soon release also our server for collaboration purposes. And we are committed to open source. We've been actively participating and contribute in the open source community and enabling the rise and the spread of SysML v2. So we had the editor tool for 2.5 years. I've been actively maintaining that. That provides the accessible entry point into SysML v2 modeling. And the most exciting news for us is that we'll be soon releasing another open source project to build up the SysML v2 community around the world. It's called Librarian, and it's going to be a library manager for SysML v2 libraries, around the world. So it's going to be like PyPy for Python, or Anaconda for Python, or NPM for JavaScript, and similar package managers for different programming languages. Okay. So let's jump into a demo. So that's what it's like to use SysIDE Modeler. So you have all the quality of life features that a modern software engineer would expect. So you have syntax highlighting, auto completion. We have documentation on Hover, where we can quickly inspect and get useful context. This Hover information can be customized through scripting. We have model navigation, where we can explore the model in ways that software engineers are familiar with. And we can define any custom validation rules as well through a scripting capability to do additional validations. And here we see now the visualization provided by Tom Sawyer, and integrated into the SysIDE modeler, where the diagrams are rendered on demand, essentially, where the views that we want to see are rendered upon trigger. So the main offering format is SysML v2 textual notation, but anytime we want to see what it's like in a visual representation, and SysML v2 has a visual representation, that the models can be represented in a visual form as diagrams, they are available. And this is a very powerful and efficient and fast way of working, because rather than focusing on moving the boxes all around and thinking about where to place them and exactly what position to choose, instead all that is handed over to powerful auto layouting engine of Tom Sawyer, and the work is much faster that way. So here we see that we can interact with the model in a visual representation interactively, and explore it, and we can even post-process the representation if we, for instance, want to share with some colleagues and similar. And what we saw just in the last, the last part is that we have jump back to source functionality, similar as people have in academic offering through using LaTeX, that we can click on a visual item, and then we can jump back to the source code, to the part where that particular component has been defined. So the workflow is very efficient and fast. Okay, SysIDE also brings a lot of AI capabilities that is essentially for us coming automatically, because SysIDE is an extension within most popular integrated developer environments, VS Code, Cursor AI, that already have powerful AI capabilities where you can choose any powerful model, large language model you want. So here we have an example of how SysIDE takes advantage of AI in Cursor AI and utilizing the Claude model. So here we just ask to summarize the system definition, and provides a narrative. And here is an example where, let me pause, where the request has been to add an additional new component to the cooling system. So in this system definition, we have the fridge definition, and we ask AI to add additional component. And what it does, based on the code base and the context, it suggests a div, a proposed change to the code base to make. And that way we can accept, or we can edit it a little bit. And this is an illustration that working with textual systems engineering models is a lot easier these days than before. And anyone who is skeptical of using textual notation for modeling, should rethink this once again. And we know, what is happening in software engineering, where large parts of code bases are generated by AI algorithms, and we have the same possibility now for systems engineering discipline. Okay, and so yeah, let's finish with this. And this last example is, for instance, that since we can script, we can define any custom rules or any custom scripts that we want. We can run on demand, through a console. So that particular one example has been just essentially apologies. That's just been That just being an example of a particular mass requirement for a fridge. And we can have that checked through a script, but that script can also run through CI/CD pipelines and check whether the mass requirements are met. So let's now go to a live demo where we will show what it is like to work with SysIDE in the system as code paradigm. So Juozas now will share the screen. Okay, great.
Yeah, so do you see it? It's fine? Yeah.
Yes, this looks good. Thank you.
Yeah, so it's the same fridge as was used previously, and this example will show the state machine simulation that the fridge, the definition of system that is a fridge undergoes. So on the left side, we can see diagnostic states with 3 states, green, yellow, and red. And on the right side, we have a simulation that is built in Python, which is enabled by the automator.
And in here we see on the left the declarative definition of the fridge, and it says what the fridge should do. And here we chosen one particular example for diagnostics definition of the fridge. So we all know what's very important diagnostic for the fridge essentially is to close the door of the fridge so that the food inside the fridge doesn't go bad. Someone needs to design it and specify that. And the way to do this is in terms of the state machine. So in this example, essentially, we define a state machine of 3 different states. The green state is where the fridge is within the optimal target temperature range. Yellow is in suboptimal, but not the terrible temperature range. Someone probably propped up the fridge for a bit because the temperature is going up, but the fridge shouldn't start beeping loudly immediately after someone propped up the fridge. And the red is where the temperature is above a particular threshold where the food is really starting to go bad quite quickly. So that's the 3 states of the state machine that's been defined on the left in the SysML v2 file. So what we can do now is immediately generate the code that will be running the state machine, and we can simulate this. And we do this through embedding the state machine execution into Python. And here, SysIDE automator has been used to simulate the state machine through embedding it into a Python state machine execution library. And it immediately, so you've seen the state jumping around between these 3 states, and we also obtained the data analysis of of how much the fridge, based on the test time series, spent in different states, green, red, and yellow. Now, we've seen everything happen very quickly and for a single click. Now, what we do as systems engineers, we should inspect what is happening, how it's performed on the test data. And we see, oh, why is it spending so much time in red based on my system specification? There must be something wrong, because this means that the fridge is beeping a lot. And we think a bit and say, oh, right, since the state machine has been only based on the temperature ranges, this means that when I close the fridge door, the temperature is not going down immediately. It goes gradually. So it means that the fridge keeps beeping even when I close the door. What we need to do is update the system definition, and we do so by adding an orange state, which checks if the door has just been closed. So we add an orange state essentially to address the issue, and it's a small update to the system definition. And then we can immediately run the same script again without any changes, and that would resimulate the same the same system now, just with additional new state, and immediately does the analysis for us. And that's where we see that this system specification, system definition update to a prototype, and analysis is happening in real time, within a matter of seconds. And that's really speeds up things a lot. And what's really important to know, this is not just for simulation and just for design space, design exploration. This can be happening in the exact same way on the real fridge, on the real physical hardware, on the real-time series, deployed in the same way through CI/CD pipelines, and we can do the exact same thing as we've seen on the real data and on the real system. So another example of the power of programmatically processing the models and taking advantage of the vast ecosystem of scientific computing, AI, and data analysis and whatnot packages within the Python ecosystem is that we can take advantage of that. So here we'll take advantage of formal verification libraries available in Python to check if our state machine has been well defined. Yes, and by well defined here we'll check for non-determinism property. So what we can do is just ask this connection with a Python state machine formal verification library to check if our state machine definition is not having non-determinism, and it turns out that it does. So it means that it's not clearly defined where in some situations which state the state machine should jump to, and we can quickly go and fix it. And we go and fix it and turn, it was a small change that was needed, and now we see, okay, the formal verification tells us that the state machine is known not to have, proven not to have non-determinism. Okay, so these are just examples to get people appreciate the power that's readily available at their fingertips through being able to programmatically access and manipulate these models and take advantage of what's available in the Python ecosystem. Okay, so let me now jump back to the slides. The last example is okay. So now is on the real world case study. So as a company, we became a tool vendor because we tried all available tools doing risk management, engineering consulting work for many years, since starting the company 6 years ago. And we worked in automated driving industry, we worked in space industry, and none of the existing tools met our needs for automation to bring maximal speed and efficiency to our clients. So that's why we built SysIDE. And one concrete real-world case study and example how our clients are already utilizing the power of SysIDE and the system as code paradigm is in this satellite constellation health management digital twin example. So here we have the V diagram flattened essentially on the bottom where we have design stage, build, implement stage, test stage, and deploy and operate stage. And during the design system definition stage, we define the system model and SysML v2. We define the reliability, failure modes, effects, criticality analysis, also known as FMECA model, as a library within SysML v2. We define the diagnostics and failure mitigation strategy, also known as FDAR, fault detection, isolation, recovery. within SysML v2 as a library, and we can also define a telemetry model within SysML v2, defining what exactly the telemetry we have in our system. And then we can use the power of SysIDE Automator to automatically generate, all the artifacts needed for running diagnostics in real time and managing them, in real time during operational activity phase. So what we then have is that the diagnostics running on embedded systems on complex satellite constellations are generated automatically. We have remote health monitoring portals generated automatically containing all the information about the system. Their failure modes, the diagnostics, and what failure modes we are mitigating, as well as the telemetry, about where the data telling us about these failures is stored, so that they can be fetched in these remote health monitoring portals. So a very simple example of a snapshot of this portal looks like this, where essentially, this is embedded into Grafana visualization system, where one has a full summary for one particular diagnostic that it has that's been all these SysML v2 models for the operator or flight engineer to use. So we have all the summary about diagnostic definition, its configuration, response actions, and we also have the context about the inputs that are coming into these diagnostics. We have understanding what failure modes are being mitigated for these diagnostics. We also have these items hyperlinked, so one can navigate and everything is connected. And then on the right, it is connected with real-time telemetry, providing historical context, as well as the current incoming data of what's the actual health state of the system and how it's been changing, and also providing all the detailed dependency structure about the diagnostics. So this is like a very simple example for one diagnostic, and it can be explored interactively. So often it's very highly dependent structures, for instance, for diagnostics management, because if a sensor is failing, the sensor failing is affecting a lot of diagnostics downstream that are using the sensor measurements as inputs into these diagnostics. So that's very important to understand all that dependency, and this is all available and integrated automatically through the system as code paradigm. So that's very powerful and very fast. This is just another illustration, from the same dashboard of the diagnostic. So yeah, and one can manage not a couple, and what we've been doing as a company has been managing thousands of these diagnostics, and this is way beyond, manual human labor in modern times to reach the speed and quality that that one needs. So yeah, that's a real world use case, and this is being used in the real world on the really important complex systems already, and our users are taking advantage of this paradigm and the flexibility and the performance of the of SysIDE for so many other things, and we can talk for hours, but it's time to stop.
Thank you very much, Juozas, to be here today and to give us this presentation and also live demo. Where should people reach out if they're interested to know more about Sensmetry or SysIDE?
It's right here. It's please come to our website for SysIDE. It's syside.sensmetry.com, and you have all the information. You can start using our tools for free. So we had an early adopter program for which you can still sign up using our link, and soon, once we go into a commercial stage, there will be a free trial available to everyone to try it out as well. We also have a very new but already active user forum where existing SysIDE users are sharing their experiences and asking questions on how to use it for particular use cases, or all sorts of tips and tricks can be found there. And our team is also mingling there as well and supporting the community. So come to SysIDE.
Wonderful, wonderful. So anyone that is interested in Sensmetry or SysIDE, you can reach out here, as Juozas just described. And if you're interested in Tom Sawyer SysML V2 Viewer, which is the product which is used to power the visualizations that you see in SysIDE, or if you're interested in Tom Sawyer Perspectives, which is the SDK and low-code development platform which we used to create the SysML V2 Viewer, please reach out to Tom Sawyer at tomsawyer.com.